Okay, so this video is about tissue ischemia, hypoxia, and basically relating how arrhythmias happen from this, and how a lot of how a lot of these things happen. Now, in med school, you spend so much time learning physiology, you spend time learning anatomy, you spend time learning pathology, but you don't spend a lot of time putting all this stuff together. That's the one thing that's missing is that you never correlate all these things, you never integrate them, you never create a web out of all this information, which is exactly what I'm trying to do. Now, let's take a look now. Okay, so when we have cells, right? Any cell, every cell here, there are certain pumps on the membranes, right? What pumps are here? Okay, there's the sodium, potassium, ATPase pump, right? Okay, now, um, taking a look at this, it's 3 sodium out, 2 potassium in. Now, what does it need to work? ATP. Okay, now where does ATP come from? It comes from the mitochondria, right? Okay, and it's actually this pump's reason why when you look at lab values, when you look in the blood, what's the sodium value over there? Around 140-ish, right? And potassium value, it's low, it's like 3.5. Okay, it's this pump that's doing it. It's pumping all the sodium out and pumping all the potassium in. Okay, now again, back to the ATP. ATP comes from mitochondria. And how in the mitochondria? The electron transport chain, right? And oxidative phosphorylation. Okay, those are the ways that we make ATP, right? Because how does that happen? We have complex 1, then we have complex 2, 3, 4, and we have 5, right? Okay. Now, what happens? NADH comes here, drops off hydrogen, right? Gives it a hydrogen, and this basically gets pumped through, okay? Inside here, we get a bunch of hydrogen building up down here, right? A bunch of hydrogen building up, what happens? It goes all the way to 5 here, right? And we have all the hydrogen here. Think of it like a waterfall. Okay, it's just like a waterfall where the pressure of the hydrogen is driving the windmill. Not the windmill, but basically the thing that turns with the water. Okay, this hydrogen will go up and through complex 5 and make ATP. But complex 4 requires something here. What does it require? Oxygen. Okay, this is what I'm getting at. The complex 4 requires oxygen, so in a sense, this whole electron transport chain requires oxygen to work. Oxygen gets converted to water, etc., etc. So that means that when I don't have oxygen, will this electron transport chain work? No, right? Okay, so that's one thing that I want to get at too. So now, what carries my oxygen around in the blood? RBCs, right? Red blood cells, and they have hemoglobin inside of them, right? Now, where does this go to get oxygenated? Well, they go to the lungs. Easy, right? Okay, they go to the lungs, and through here we have these the capillaries. The RBCs come by. There's oxygen in here and carbon dioxide, right? It gives off carbon dioxide and picks up oxygen. Okay, does this thing. Okay, now it leaves the lungs and it goes to my different tissues, right? Let's say it goes to my myocardium, my heart tissue, right? Goes to my heart tissue. This is a myocardial cell. Goes to my myocardial cell. The RBC comes here. It's filled with oxygen, and it's going to drop it off. Okay? It's going to give the oxygen. Now, let's say I have hypoxia. Let's say I have some problem oxygenating. Let's say I have a stenosis, basically where the blood vessel which is supplying the myocardium, is stenotic now. It's stenosed. What does stenosed mean? Basically narrowed, okay? So that RBC coming through, it can't fit through. If it can't fit through, what's going to happen? Can that RBC come by to give the myocardium any oxygen? No, it can't come by to give it any oxygen. Well, if that myocardium doesn't have any oxygen, can it complete its electron transfer chain? No, it cannot. Remember, no oxygen, no electron transfer chain. So if it doesn't have any oxygen, and if this chain can't work, can I produce any ATP? No, I'm not producing any ATP inside my cell here, right? Remember, this is a mitochondria inside the cell. If I don't have any ATP, can my sodium-potassium ATPase channel pump work? No, it's not working anymore, right? Because it doesn't have any ATP to work for. Now, if this pump's not working, can I pump sodium out now? No, I can't pump sodium out. So what happens? The sodium builds up inside, builds up inside. And can I pump potassium in? No, I can't do that. Potassium stays out. So if sodium's building up inside, what's happening to my osmolarity inside the cell? It's increasing. It's increasing, right? All the osmolarity is increasing because the sodium's building up. Well, if my osmolarity is increasing inside the cell, what's water going to do? Is it going to come inside the cell or go out? It'll follow, right? Remember, water will always go wherever there's higher osmolarity, where the party is, right? If water is going inside the cell now, and there's higher sodium, higher osmolarity, what's happening to the cell? It will swell. It'll get bigger, right? Because water is filling it. Water is filling it. Now tell me something. If I have a myocardial cell, and I have a lot of water in it filling up with it now, do you think it's going to be better at conducting electricity or worse? It'll be worse, right? Because when cells are swollen, their nerves are, the tracks that they're on and everything, it's not good. So the cells swell up, the conduction gets messed up. That's why when people have acute myocardial infarctions, their cells are damaged here because of, the low oxygen, etc. That's why they get arrhythmias, right? They're so prone to arrhythmias is because of all the cellular damage. The cell damage, cell swelling, and all stuff. And remember, when cells become ischemic, can they maintain their membrane here? No, they can't. It's really difficult for them to maintain their membrane. Their membranes become really, really weak, right? They become weak. Now, every single cell has antioxidants. Okay, this is vitamin E, and the whole glutathione, peroxidase, all that stuff. That is an antioxidant. Why do we need antioxidants? Because oxygen, when it combines with other oxygens, makes free radicals. What are these free radicals like doing? They're pretty bad. What they like doing is they like going and damaging this membrane here. They damage membranes, okay? Well, what's the big deal? Well, the big deal is this. Let's say I have a heart, right? Let's say I have a heart muscle, right, and a cell. Okay, and I have a specific blood vessel that brings blood to the cell, okay, my RBCs. Now, let's say this becomes stenotic, or like there's an emboli, or thrombus, or something that happens, and I have an acute myocardial infarction, basically ischemia to my heart muscle. What happens? Well, since my cell is ischemic, it's damaged. Can it produce those antioxidants? No, it can't, right? It can't produce those antioxidants. And what's happening is this cell wall, all the myocardial cell walls, they're becoming weak and damaged. Okay? They're becoming really, really damaged and weak. Damaged, right? So, have you ever heard of reperfusion injury? What happens in reperfusion injury is that, well, we had an emboli, a thrombus, that basically was occluding one of my arteries, let's say my left anterior descending artery. It occluded it, and my heart cell spent some time without any oxygen. And in that time it spent without oxygen, my cell walls became really weak, really weak. I'm not producing any antioxidants, okay? Let's say I give them TPA, tissue plasminogen activator. Again, it's kind of like Drano, all right? It's a clot buster. It'll bust the clot. So now I bust this clot open, okay? This clot is completely open now, okay? And what's happening? I'm getting really oxygenated blood here. A lot of oxygen here, a lot of oxygen in this cell. If I have a lot of oxygen in the cell and I don't have any antioxidants, what's going to happen? I'm going to form what I talked about before, free radicals. What do these free radicals do now? They damage the cell membrane more. They just eat it up, poke holes in it, puncture holes, and I get cell lysis. That's called reperfusion injury. Okay? They love asking questions about this, and they'll give you a scenario. They'll give you a 50-year-old guy who comes in with acute MI, etc., and they'll mention these things, and the answer will be reperfusion injury. How will they ask it? They'll say that a 50-year-old guy came in with acute myocardial infarction. You gave the patient TPA, and 30 minutes later he developed arrhythmias. He developed increase in his CK or MB levels, etc., or troponin levels. Why? It's because of reperfusion injury. That blood came back when you reperfuse the patient, really oxygenated blood, a lot of oxygen, damage the cell membrane even more, and cause damage. Okay.